So thank you, everybody, and welcome to this presentation on 5 Java features you didn't know about. And the subtitle is Number 4 will shock you. This is funny. So, I'm Per. I've been around since Java 1.0. I've been in more than 40 talks around the world. I was a co-author of the publication Modern Java, and also wrote articles in the Java magazine.
And I'm Dan.
Yeah.
I also work at Speedment.
Okay. So let's go back to the good old days. What is this? Apparently, this is some kind of POJO called A, with a few properties, A, B, and C, 2 strings and 1 int. And if we just look at the comments, we can get some more clues what this is. It's a person. And we have a first name, last name, and social security number. And why would we ever want to use a class like this? We are evidently sacrificing clarity for performance. Why would we ever give up so much for that? Yeah, because this was back in the days before the JIT compiler. So actually, the code ran 30 to 40% faster if you have shorter identifiers, because the JVM had to interpret all your code. And of course, there was huge problems. I mean, think about the stack traces we had. What is that? And let's talk about reflection. I want to even go there. That was terrible. So let's talk about allocating objects on the stack. How many of you guys have actually allocated Java objects on the stack? Some of you. Ah, good. Let's see if we can do this poll after I've told you about it and see if there are more people doing that. So the idea is, of course, to instead of allocate objects on the stack on a big heap, like 16 gig or something, and we have to allocate them, we have to use them, and then they have to dispose of them. That's a quite long and complex procedure. Why not instead allocating on the stack and use them and inherently throw them away? Because when we pop the stack pointer, they go away automatically, and the stack is much smaller than the 16 gig of global heap. So let's look at the problem. Let's say we have this immutable class with 2 properties, x and y. We have a constructor, and we have 2 getters. And we have a 2-string method. Let's zoom into the 2-string method here. And I know that this is not the recommended way any longer to write a 2-string method, but for the sake of argument, it shows a lot of things I'm going to explain. So we create a string builder, we use it, and then we create another object, a string, which of course has to be detached from the string builder because we don't want to be able to modify it afterwards. And then we can create a point like this, and we can use it. In this example, we invoke the sum method, and we will iterate 1,000,000 times. We will call the 2-string method and compute the length of it, and we'll sum all that length. So will this create 1,000,000 string builder and 1,000,000 string objects? That is the question. And the question is, it depends. It depends whether we can observe those objects or not. So this sounds a little bit like quantum mechanics. We're going to see some similarities with that. So let's try to push a little bit further into it. Let's start our Java program. We do a garbage collect to clean up the heap, what's there from the startup. We invoke the sum method. We invoke the garbage collect, and we invoke the sum again. And let's see what we have on the heap. So after the first invocation, we have something like this. We have like 52,000 objects of type string and 30,000 of type string builder. So evidently, we created a bunch of objects. After the second invocation, the string builder is nowhere to be seen. We don't create any string builders anymore. And there are just a few strings lying around, presumably those strings that were there from the beginning when we started the JVM. So it's like a Russian Matryoshka doll. When we do something called escape analysis is something that the compiler does. It derives that a string builder object cannot be observed from outside. It cannot be observed outside the method, and it cannot be observed by another thread. And because of that, we can kind of hide this smallest doll into the second smallest dog, because we cannot observe it anyhow. So this is actually what the compiler does. It allocates this object on the stack instead of on the heap. automatically. We don't know it, but it happens behind the scene. And that is good. And it gets even better because the compiler has something called inlining, which is that you kind of flatten out your invocation and methods so you can observe optimizations over a broader span. So if you look at the map operation here, actually the string and the string builder is local in that context. So we can even hide two dolls within this scope. So that means that we can allocate both the string builder and the string itself on the stack. And that's good news for performance. And if you look at the entire scope, actually if we create this immutable object and we iterate 1 million times, and we can see that within the map operation, point to string will always return the same result, the length that is, and it's about 10. So in the best of worlds and in some distant future, the compiler might just return 10 million as an order 1 operation in this case. It's a theoretical opportunity, but we're not there yet. So what happened? Well, after 10,000 calls, the JVM compiled the toString method. It gathers statistics of all invocations, and then after 10,000 calls, the compiler is invoked. So after a while, after it has compiled, the old code path was replaced. And that took a while, so after 50,000 calls, the compiled code was activated. So it's like we're running on this left-hand side. That's the commuter train, which is interpreted. And once the compiler did its job, we switch over to the express lane, the right-hand side. And our code runs much faster. And this explains why there were 50,000 objects and not 1 million objects in the first run. It also explains why it was 0 objects in the second round. So after all, it wasn't quantum mechanics. And that's good, because who understands that? Actually, it's a standing joke among physicists that if someone tells you they know exactly where quantum mechanics is and where it's going, they don't. But that's only funny if you know the Schrödinger equation. OK, fast facts about stack allocation. It creates a representation of an object rather than on heap, on stack. And a stack objects, they are allocated instantly without memory allocation. And I mean then heap memory allocation. Of course, they're allocated on the stack. And they are inherently cleaned up when they go out of scope because we pop the stack pointer. And they can be simpler than the heap counterparts. They don't have to contain all the bells and whistles of ordinary objects, like, for instance, class pointer or synchronization primitives. And when we talk about synchronization, they can be totally removed because the objects that passes the escape analysis cannot be observed by another thread. And thus, we can remove all the synchronization statements. So if I would have used a string buffer, which is a synchronized version of a string builder, the compiler can remove the synchronization and effectively turning the string buffer into a string builder. So that's good. I don't know why that picture is there, but it's nice. OK, another cool thing is that the stack is very likely to be cached by the CPU because it's used all the time. So it promotes a higher degree of locality. Instead of reaching out to the heap, we can use the stack more, and it's more local. And it's the C2 compiler which performs the stack analysis. So if you want to use it, make sure you run in server mode. It can kick in after 10,000 invocation. That's a little bit out of the scope exactly when it's invoked, but by default, it's around 10,000 invocation. Depends on what kind of Java version you're using. And escape analysis can span several call levels. So you can kind of do it digging down your code. This is an important thing. If you're overriding finalize, this prevents stack allocation. And why is that? Anyone knows that? It's because the finalization is done by another thread. So if you override finalize, then the compiler will determine that this is identifiable from another thread, and thus it can't be allocated on the stack. So many people have said stay away from finalize, and this is yet another reason to stay away from that. It also allows scalar CPU register representation of integers and longs. They don't have to create object for that. And it explains why returning an optional list is comparatively cheap Some people think that, oh, if I wrap my variable in an optional, my code will be slow. But it won't in most cases. It also explains why streams can be that performant, because usually you have map operation, like in my example here, and those objects are never created on heap. They are created on the stack most of the times. And even if you use Grail VM, I know there was a talk about this earlier today, it will be even better because it's much better to do inlining and escape analysis. So in sometimes it's even like 100% faster. Good news, it promotes local abstraction, and we don't have to sacrifice code clarity for performance. So Dan, it's you.
All right, thanks. Yeah, for proper performance testing, as we call this second item here, micro-benchmarking is typically described as unit testing, but along a different dimension. So if you would have unit testing for behavior, you would have micro-benchmarks for performance. And since they are similar in those aspects, they also share other properties. So you can use both for failing early, in the sense that you can actually analyze a subsystem or a unit and find out problems within it without having the whole system at hand. It can also be used, both can be used to assert that future versions will be performant, both in the ways that the unit test will describe an invariant, a functional invariant, in terms of saying that, well, for this predefined set of inputs, we will always get this output. Now, the micro-benchmark can do the same thing when it comes to performance, saying that this super smart algorithm with my super smart data structure will always outperform a naive implementation with a linked list, for example. And there you have this invariant also for the future in the same way as for the unit tests, if you include this in your continuous integration, for example. Another major use case for unit tests, and therefore also for micro-benchmarks, may be to reproduce problems. So you have a production system where you have a problem, and it's a typical use case then of using unit tests is to reproduce a problem and then solve it, and then you would have this test to make sure that there won't be any regressions. And for the similar thing along the dimension of performance, you may suspect that some subsystem of your whole system doesn't perform as you would like it to, then you can express this in terms of a micro-benchmark. For example, as I said, my super smart algorithm should actually be this smart, and then you can state that and make sure that it stays that way. Then micro-benchmarks, of course, also is there for exploration. Actually finding out, is this super smart algorithm actually smarter and more performant than this one? Perhaps the typical use case may not be that you have two super smart algorithms to compare, but a more realistic one would be that you have your own super smart implementation. You want to compare that to a naive implementation with perhaps a linked list. And you want to make sure that, well, when I add this maintenance burdens that comes with super smart algorithms, at least that's my experience from my super smart algorithms, that they do cost in terms of maintenance. If I want to justify that, I want to make sure that I actually add some performance to, and you can use the micro-benchmark for that. So the micro-benchmark harness is there to help us control the environment to do this. And with the environment, I mean several different aspects. Sometimes the performance of an algorithm has to be measured while there is concurrent load. And then the micro-benchmark harness will help us out with a method called consume CPU. And I mentioned that because I want to show the code in the next slide. Then statistical noise, of course, measuring time. There will be a matter of chance there, so you will need to speak of the results in terms of statistics. And then, as Per just mentioned, the C2 compiler. We want our micro-benchmark to represent what would happen in a production system, right? And then, of course, we want the micro-benchmark to actually test the real situation. The real situation is where the C2 compiler has kicked in. So therefore, the micro-benchmark harness will help us out with adding some warm-up so that we get this 10,000 rounds of computation. And then you also mentioned that the compiler is super smart about inlining and escape analysis, and that is great for the production system, but it is a huge problem if your test actually collapses into something that is trivial, because then you're not testing what you wanted to test. So the micro benchmark harness will help us out with that, and it has to do so in a careful way, not to introduce probing effects, because whenever you want to measure something, you will also affect it, but you want to minimize that. So you don't want to mess with caches, and you don't want to create a lot of lock contention or anything like that while doing so. So here is the code example that I promised you. That's the consume CPU method, and it does this very same thing. So it takes a long as input, and it's then supposed to consume CPU cycles in a linear relation to the input value. Of course, then all you have to do is spin a loop for that many laps. But then to make sure that this is not collapsed into nothing, you need to make sure that you pretend to compute something of value. So you start out with a value that it cannot be determined statically. Instead, you start out, as you see, with a timestamp and then go on. Then you do something in the loop that cannot be statically figured out. And then the punchline, the last thing here, is that we make sure that we cannot say that if the last thing wasn't there, we would say that, well, t doesn't escape this method, so t doesn't have to be computed. But here we make sure that, well, there is a chance that t escapes by updating the static state. And as you see, we have a long that we have changed quite a lot. So that long actually happened to be 42 is highly unlikely, but it may happen, and therefore it cannot be optimized away. So let's go for just a short little benchmark. We want to sum integers in a stream of integers. And we use 3 different approaches. We use an atomic long, a long adder, and then the accumulator approach of having a stream and creating an accumulator that can add items, and then finally accumulators can be merged into a final result. And the accumulator is a rather trivial thing. As you saw, what we do there is that we return values from those methods. Obviously, returned values do escape the method, so that's not a problem. But it could potentially be a problem that all the intermediate results could also be optimized away. Since we use a predetermined stream of integers, actually it's a constant that you are computing, so in theory it could be collapsed into a constant. So if you want to make sure that also those are being consumed, you can use a black hole. And what we do here is that all the intermediate results are being consumed, and therefore we make sure that this happens. This is not needed, but I wanted to show you the principle of the black hole. It's not needed in this particular case because it doesn't affect the result in any significant way. And we add 3 more. The parallel versions are the ones that we had before, just adding the word parallel to the stream. We start out the benchmark, and there you saw, or you didn't really have time to see because I clicked a little bit too quickly, but you will see warm-up, and then you will have a progressing of this test which lasted for some 40 minutes. And then we have these results that can be visualized in this way. And I just want to point out to you here that we start out with the streaming implementation is more efficient both for the single thread and the parallel version. And that's kind of expected because it doesn't need any synchronization at all. So that's a super efficient way of solving a problem that can be divided into sub-problems that can then later, in a feasible way, be merged into a solution to the whole problem. Then the adder is not very great for the single-threaded version, but can really utilize more threads added. But the atomic one is slightly more efficient for a single thread, but then adding one more, well, that's a shocker. Yeah, yes. You know, you really lose performance when you add more threads there. You wouldn't expect any more performance adding more threads to that thing, of course, because there can only be one thread updating that thing at a time. But losing this much performance perhaps qualified as the shocker. So just to wrap this up, we don't want to clock, we want to do benchmarks. We want to outsmart the JVM in the sense that we should make sure that the compiler doesn't optimize the whole test away. And then I want you to remember for a little while, that won't be a test, but I will be mentioning this later, so therefore I would like you to remember it for then, that collecting a stream is a super efficient way of parallelizing a solution of a problem, because you don't need any explicit means of synchronization.
Cool. Talking about stream, we go to the next issue. Short circuit in stream for massive performance gain. That's a big promise. So suppose we are at A, and we want to arrive at B, but there is a complicated path in between. And now the rhetoric question is, wouldn't it be better to go this way?
Seems so.
Yeah. So what do I mean with that? Well, we have this problem here. We have a list with 3 elements, and we can compute the size of the list. It's obvious that it's 3. And also, we can look at the complexity of this operation. For a normal list, the complexity is order 1. That means that it doesn't matter how many objects we have. It will still take the same time to compute the result. So if we have 3 elements, or if we have 3 million elements, it doesn't matter. But if we do the other way, if we create a stream and count it, it's actually order n. So if we have 1 element, the complexity, and we will iterate 1 time, but we have 1 million elements, we will iterate 1 million times. And that's bad. So that is part of the problem. Let's talk about declarative construct. A typical SQL query is a declarative construct. This instructs the database that we want to count the number of rows in the film table that satisfies this requirement, or this predicate up here, where rating is PG-13. The database is then free to use any means it has to produce that result. It can iterate over all the rows, but that's unlikely. More likely is that it will use an index. And in some cases, it might have even pre-computed this result. The same is true for streams, though, even though it's not so apparent. But the first statement up here, films stream, produces a stream that represents a stream of all elements of all films. And next chaining command filter says that we want to create possibly another stream that only contains those elements. It doesn't say that we want for each stream evaluate this predicate. That's a big difference. So streams are also declarative, and then we want to count them, of course. So in theory, a smart framework can take this stream and render the SQL query up there. Nothing prevents that. And in fact, I will show you that's what's happening in the Speedment case. So we can have a way of looking at streams at either glorified iterators or kind of more smarter streams. And it's up to you, actually, what you want to use. So this is a small solution. Here I'm trying to implement my own list, and I don't show every method here. I only show one method, which is a stream method, which returns a specialized implementation of a stream that actually returns the size of the list. So for my stream, for my class here, the complexity is order 1 for the size. Of course, it will only work if I just call size, not if I do filters or anything else in between. But that can be solved. So I can go about and improve my custom stream. So for example, if I can kind of move away the skip operation. So when I had a skip 1, in this example, I can move that and merge that operation into the source. So instead of using a backing list, I can use a sublist of the backing list. And so I have eliminated the skip. So if my stream count is order 1, then stream skip something count is also order 1. And I can continue to do that and chop each method off as I go along. And eventually, if I'm lucky, I have implemented a kind of safe stream that is always order 1. Is this really legit? Yes, in fact, from Java 9, we have this API note regarding streams that says that if we can optimize away elements, they will not be seen, for example, in the peak operation. So this is not something that's even desirable, I would say. So let's take an example with Speedment. Here I have a stream of all films. I'm only interested in the rating PG-13 and films that aren't short films, films that are longer than an hour. And I want them sorted in film length order, and if they are the same length, I want a secondary order in title in reverse order. I want to skip the first 50 and then look at 25. This is some kind of paging system, and then I want to do something with it. In this case, I just print them out. And Speedment is able to render this to a complete query and merge all the stream operation into SQL. And this example is MySQL, but if it would have been another database, it would have looked a little bit different, but we don't have to care about that. So that's cool. You can take it for a spin. It's all open source. So if you want to learn and improve it, you can do that. It works for pretty much any database. OK, so let's look at the facts. Source-aware stream that can merge stream operators into their sources. Java util stream is just an interface, so you can implement your own streams if you want. In principle, for example, anyone can implement the thing I was trying to show here. As a home lesson, you can implement a utility method that takes a stream, an existing stream, and returns a list and returns a stream, which is smart in some sense. I should, though, warn you that it's not easy to implement a stream correctly. You have to consider parallel cases. You have to consider sometimes the entire pipeline. What you do, the order is significant, and there might be some mapping instructions that are tricky. You have to prevent reuse, because if you have a stream and you create another stream, the old stream that you kind of took off must be blocked from usage. You can't reuse them. You must handle close handling properly. What happens if you have exceptions? And you have to release any potential resources, like a database connection or a file handle or whatever you have as a source. And it easily fans out to special implementation of int stream, long stream, and double stream. So it's a challenge, but it's up for grabs. And it can vastly increase your performance, both sequential and parallel, of course. One thing, a little warning is, though, how do we know what's happening? How do we know that these super smart streams really are super smart? Well, in the case of Speedment, you can just enable logging and see exactly what's going on under the hood. And I think also in other cases, it's smart to kind of open up what's happening, because otherwise you don't know. It would take 1 hour or 1 millisecond. And it allows us to use declarative code, clarity, without sacrificing performance. So that's, again, a mantra here. And that brings us to the next point, which is holding terabytes of data in the JVM with no GC impact. So this is an example of a garbage collector. I don't know if this is slower than the JVM. Sometimes it's not. Depends on what you do with it, actually. So this is the problem. Suppose I create a huge map. Here I iterate over a billion times, and I create a billion films, and I collect them to a map based on the film ID, and then I just take the film object and put it in that map. This is a big problem because it creates a lot of heap problems. It will create a lot of extra objects. For example, the int there had to be wrapped into an int object. There must be a lot of map entry and maybe internal lists, stuff like that. So that will create a lot of objects. Maybe you have like 8 objects for each film you're putting there, depending on what kind of map you're using. Each object is subject to overhead and byte alignment. And the lifetime, if you create such a map, it's likely that it will live for long. So, but each time the GC is invoked, maybe you don't have to look at each object, but it's still a consideration for the garbage collector. And it's difficult in this case to retrieve objects based on something else than just a key. This is just a key value, so you might end up with adding a lot of tree maps, and then you have even more garbage and objects lying around unnecessarily. And the problem is that the execution time as a function of the numbers of objects you have is not linear in most implementations of a garbage collector. So it's kind of this cocktail party problem. If the number of persons double, you have to shake hands with 4 times as many people. And it's the same in some implementation, or in fact, the most commonly used implementation of a garbage collector has that kind of quadratic complexity. So depending on the average object size, we will kind of run into the wall somewhere around 16 gigabytes. I think in the recent implementation, it's been improving, but still there is a wall. We only hit it later. So how can we solve that? Well, on a higher level, we can just take the heap, put some things off heap, and then that will be smaller because we don't have the overhead, and we will end up with a really small heap. Wouldn't that be fantastic? But how can we do that? Well, first of all, we need to be able to allocate memory off heap. And that can be done in many ways. The two fundamental ways that are common is using ByteBuffers or using Unsafe. And a ByteBuffer can be obtained in various ways. These are 3 ways. I think the upper is the most preferred way of doing it. So in this case, we allocate a ByteBuffer off heap. You can also map a file, or you can allocate an on heap. And you can use Unsafe to allocate as much memory as you want. So if we look at the pros and cons, ByteBuffer has a size limit. It's limited by the int representation for indexing. It's 2 to the power of 31, whereas Unsafe is unlimited, and then I mean virtually unlimited. The day we pass 64 bits, we might have other problems. ByteBuffer has range checking, whereas Unsafe doesn't. ByteBuffer is zeroed. It's guaranteed to be zeroed out, whereas you get what you get in Unsafe. It could be zeroed out, but it could also be reused. ByteBuffer is a bit harder to clean deterministically because you have to invoke the cleaner. It's a little bit different in different Java versions. And a little warning here is that if you use a ByteBuffer in a map, for example, the hash code actually looks at every byte of contents. So you have to make sure that you use some kind of wrapper objects, or your maps will be really slow if you have big ByteBuffers. So let's talk about Unsafe. Unsafe is unsafe to get because it depends on what Java version you're using. Unsafe is unsafe to use because there are no range check. Unsafe is unsafe not to use because if you get to call free, you have a memory leak. And last but not least, Unsafe future is unsafe. So I think they picked a pretty good name. In fact, they're working on the replacement of Unsafe and memory allocation as we speak. So this is kind of geek territory. So you should wrap if you use Unsafe, make sure you wrap it in something. If we look at the performance, off-heap is better than heap memory because it's less protection. And Unsafe is the fastest, but then you have no safety. So I think off-heap in the middle there, ByteBuffer is a good compromise. You can easily write a hello unsafe program. You use unsafe put byte 0, 0, and this is very likely to produce a segmentation fault. So don't do this. Don't try this at home. So my recommendation is consider using ByteBuffer over Unsafe. Consider, I said, there are some rationales to actually use Unsafe, but those are rare. Having allocated memory isn't enough. We must also be able to use it. And when we use off-heap memory, we often use something called a serializer. A serializer can write and restore objects from off-heap. So it serves like an intermediary object. So in this very simple case, we have a method called serialize, which takes something of type T and puts it, flattens it out in the ByteBuffer, and as a side effect, changes the ByteBuffer's position. It also has a deserialize method, which takes a ByteBuffer and that said position, and is able to restore and reconstruct that object. So this is a very simple serializer. I wouldn't recommend using this simple scheme, but this is the principle how it works. So, for example, if I want to implement my point serializer that I talked about before, it's very easy to do. I just write down my x and y coordinates, so this would be very efficient. I just write out the bytes in memory, and when I deserialize it, I just go there, read the x and y, and construct a new point. So it's very easy. Note that the upper method is not thread safe, whereas the deserialize is thread safe. So that's one example of why this simplified version is not really good in reality. So, of course, I'm going to talk about Speedment again. So Speedment can do all this for you for free. So if you have a slow application, you want to get rid of that, you connect to your database, enter your credentials, and Speedment will download the metadata model for you. On the left-hand side, you see all the tables and columns. And you can change stuff, but you can also press Generate directly. And this will generate a complete domain model for you. And now you can use your streams like this directly. So you can view your database as streams. And using sorting and filtering and whatever, in this case, we collect a lot of employees into a list. And that's all good. But if we run it against the database and it's still slow, we can use Off-Heap memory to create snapshots from the database up into the JVM itself. So you can have like a terabyte of data mirrored up in the JVM, and you can let your queries go to the in-memory representation rather than go into the database. And you can create continuous queries. And this way, you can be like 1,000 times faster or lower latency. This is, of course, good for analytics time of queries and not transactional data. OK, so how do you store table data? We generate POJOs and serializers from the database metadata. And a single table consists of one or several off-heap ByteBuffers. Of course, if we have just a small table, we only need one ByteBuffer. If we have a huge one with billions or trillions of rows, we need to have several ByteBuffers because of the 2 to the 31 limit. And serializers support something called in-place primitive deserialization. So for example, if I serialize my point class, I can extract only the x coordinate without constructing the entire object. So I can work directly in off-heap memory. That's very important for performance reasons. And also indexes are off-heap. And they provide a lot of operations like is null, equals, less, greater than, not in between, starts with, and all those things. And they are all only order 1 or order log 1. So they're basically constant regardless of how much data I have. And all the tables and all the indexes are combined into something called a DataStore. And the DataStore contains an immutable snapshot of data. So it can't be changed. And that's good for performance reasons and for thread safety, because it's inherently thread safe. A new snapshot can be created on the fly. So if I just change something little, I can recycle most of my ByteBuffer and just change 1 or 2 ByteBuffers and then create a new view of all those ByteBuffers, almost for no cost at all, even though I'm working with terabytes of data. And it can fully decompose a stream into JVM memory with primitive operations. So let's show you this one. First, the upper one. I create a stream. I filter out the rating, PG13, and then I count them. And actually, this will have a latency of 160 nanoseconds, an average on my laptop on Java 8. And to put that in perspective, just accessing 64 bits of memory is 100 nanoseconds. So I think that's quite impressive. The last one is more complicated. Here we apply 2 filters. So there is some kind of a query engine that will provide the most optimized filter to use in this case. And the map to int is kind of this in-place deserialization operation. So it's able to go to Off-Heap and just grab the int and do this summary statistics. Summary statistics is a standardized Java stream operation. So you can use the entire ecosystem of streams with this. And if we run it for different JDK, we will soon see the shocker. It's the Grail VM. It's 100% faster because it's escape analysis and C2 compiler is much more advanced. It's written in Java, and the old ones are written in C++ and are kind of hard to maintain. So I think you guys should really try Grail VM if you want performance. And that's it. So that's
right.
Your time.
Thanks. Yeah, I guess some of you may have wondered why we choose to have exactly 5 items on the list today. But now, as you can see here, we are working with progressively wider headlines all the time, and now we've reached the limit. Oh. So I'd like to talk about the idea of having, Per has now described, how we can store data off-heap and reasoning about that via streams. Now, let's consider a case that we want to perform an aggregation on data, and that the intermediate result that we are computing actually requires quite a lot of memory. Then it would be very nice to have this intermediate result off-heap, and then just have the final result on-heap. So to use a similar picture as we've seen before in the first part of the presentation. We move from having everything on the heap to some parts of it off heap, and then we do the calculations off heap, and then finally we just materialize the final result. So as a simple example, let's say that we have a population of persons and that we want to calculate the average salary per age group. Then our data can be described by this person object that we have on top, and then we have the age salary, which is the result. And then this result constitutes the interface between off-heap and on-heap data. So that is actually what will be materialized on the heap. The other parts will not be. And the way that we express this in the API of Speedment is that we create an aggregator. We do that via a builder pattern, where we start out describing the getters in the source, which in this case are persons, and then we have the destination values that are being put into the destination objects that we have. We build that aggregator, and then that aggregator can be used to consume a stream of persons. And that is why I wanted you to remember this idea of being able to parallelize things and actually using streams and consuming streams and collecting streams via a collector as a very efficient way of doing things. I'll come back to that in a little bit later. And what you saw before was a very simple example where we would just create the average, but via a composition of functions, we can also create more advanced functions that are being computed off-heap. So this is just an example of computing the BMI, for example, by doing a few operations on the data. And the idea here is that the aggregator that is being built here will be able to do all these things off-heap and not create anything of the intermediate results on the heap. And the performance of this will be superior because of the GC impact being much less, no matter which kind of garbage collect you have, of course. I mean, you may be thinking that, well, I'm looking at a very efficient next generation garbage collect where the number of objects is essentially of no problem. But then, of course, it is more efficient not to have things on the heap at all, but instead just materialize the very results that you're looking at. And if you just add parallelism to your stream so that you allow your stream to feed these persons, in this case, in chunks that can be handled parallel, then you will get a very nice performance boost because you can use all those threads at the same time. So what you saw before was our aggregator using getters on persons. And perhaps some of you would say that that was a silly idea, and then you would be right. Because the silly thing about that idea is that, well, then you would need a person in the first place, right, on the heap. So to be able to call a getter, you would need an object, and that would defeat the whole purpose. So that was more of a pedagogical device that I used to be able to transition to this idea instead. So the on method that you saw before is overloaded. So instead of having getters on persons, we can use this instead. And as you see here, we use person age and person salary, which are generated by Speedment at design time from the metadata of the person. And they contain enough information for the runtime to deduce how to extract that very data from a serialized person. And then we can add parallel in the way that we showed before. And since computing averages over these buckets can be very easily parallelized and then merged together, this will be a super efficient way of computing this aggregation, both in terms of heap load, but also in terms of parallelism.
So that completes our presentation. And if you want to reach out to me or Dan and want to engage us in helping you to increase performance in your application, you have our emails here. If you want to play around with Speedment, you can do that there. And then you can also find Speedment on GitHub if you want to look at all the source code. And you can come to my talk tomorrow, where I go more into details about this DataStore query and how things are really dealt with off-heap, more into the gritty details. And that's tomorrow around 9 o'clock. So thank you very much.
I think if there's a question, we can take it, or you can come up here. Everyone wants to go to fika. Okay, thank you.